A smooth roller P of mass m equals to 0.4 kilogram moves along a grooved horizontal slot as shown. The slot is in a spiral form defined by the equation r equal to 0.12 theta meter, where theta is in radians. Knowing that arm OA is rotating at a constant rate theta dot equals 3 radian per second, determine at the instant when theta equal to pi radian, A, the free body and kinetic diagram of the roller, B, the force exerted by the arm on the roller, and C, the force exerted by the wall of the slot on the roller. The slot is horizontal. It is rotating like this. The arm is like this. You are going to use r-theta coordinate or radial transverse coordinate. We are going to analyze at pi equal to pi rad. Pi means 180 degrees. So it means at this situation. So I'm going to put the axis in this situation. So I put theta positive because we know that this arm is moving anti-clockwise. From here, it will go down. And r is positive since I put the origin is at the center here. Point P is not in the middle of this arc. Point P is a little bit above. So the motion of the ball is not going downward, but the tangent is inclining. Let's start with kinematic equation. The expression of r is given in the problem. So having r, you can calculate r dot. You differentiate with respect to time. So r dot equal to 0.12 theta dot. And then r double dot is 0.12 theta dot. And you have that theta dot is constant, 3 radian is stated there. So when theta dot is constant, it means double theta dot is 0. So it means r double dot is also 0. When theta equal to pi radian, you obtain r 0.38 meters. You put the value of theta inside the r dot, also you have this one. So I have these values. Now I'm going to write radial and transverse component when theta equal to pi rad. AR equal to r double dot minus r theta dot square. That is the radial component of acceleration. If you put the values, r double dot is 0, and then theta double dot is 3, r is 0.38. So you have AR. We have negative, it means AR is going to the right at this position. This is the theta component of the acceleration, the transverse component, r theta dot plus 2 r dot theta dot. You put the values, you obtain 2.16 meter per second square. At this position, the acceleration is going down. So we have the kinematic. Let's go to the kinetic part by drawing the free body diagram. We are going to focus on the roller there. That one. We are going to draw forces. We follow this direction. So I'm going to draw the axis here. So one is vertical following the theta, one is horizontal following the r. From the vertical, you have the force exerted by the arm. The arm is pushing the roller, pushing downward in this drawing, perpendicular to the arm. Okay. While pushing, there will be resistance from the wall of the slot. So that is the tangent to the motion. We know the motion is the dashed line. Here we have the tangent a little bit inclined. So if there is friction, the friction will be in the tangent direction. But the friction due to the normal is the reaction from the wall of the slot. So if there is friction, the friction is in this direction. There is no indication in this problem regarding the friction. So I put assumption, no friction on every contact. If I put this assumption, I can neglect the force friction. And then the normal, that is normal to the tangent. So that is the reaction from the wall of the slot to the roller, NP. Let's say this is the angle, alpha. This alpha, of course, it is there as well. So when you don't have perpendicular forces, you are going to project. In this case, I'm going to project NP. NP to the horizontal, it becomes NP cos alpha. And then to the vertical, it is NP sine alpha. Let's bring it there. This is the free body diagram. Let's solve the alpha. So let's focus on this right triangle and bring it there. We have a right triangle where the angle here is alpha at point P. This side will be dr. This side will be r delta theta. Tangent alpha is dr over r d theta. You have the expression of r. Differentiate this equation with respect to theta. So you are going to replace dr over d theta with this one, and then you replace r with this one. So you have tangent alpha equal to 1 over pi. We have the value of angle alpha, 17.66. Now we are going to focus on the kinetic diagram. Now I see from the acceleration point of view. We have calculated in the kinematic section that this roller has acceleration in the r direction and theta direction. So in the r direction, MAR, and also in the theta direction, MA theta. I bring it beside the previous one, so I have free body diagram and I have kinetic diagram. Both must be equal. Sigma F equal to MA. Now let's solve it one by one in each direction. We start in the direction of R. We have here NP cosine alpha, and we have here MAR. Okay, so you can put the value, you can solve NP. That is the question C. The force exerted by the wall of the slot on the roller. This is the answer. Negative. Now in the theta direction, I assume positive is downward following this convention. So in the positive, I have NP sine alpha going up, and we have MA theta dot going down, right? And then FP going down. Going down is positive, so FP minus NP sine alpha equals to MA theta. So we have the force FP here. That is the force from the arm pushing the roller. So having this, you have answered the problem.